Hello, math fans. I'll make a video here on how we set up so-called word volume problems. These are ones that come up in the homework where it just describes the boundaries. And I find that students are often overwhelmed by just the sheer number of equations here. Look, there's 1, 2, 3, 4, 5 equations. They just are like, Dr. Lovelace, you're a huge jerk. I hate you. I can't believe they say that to me. They say, why do you do this? Why are you so mean? Why are you so ugly? All the things they normally say. But anyways, find the volume of the solid bounded by these things. Just in 3D, there's a lot of boundaries. It really would be nice if you had a plan for how you approach such a problem. And I have that for you. And in Math 126, we make it a little easier because we're going to always have z be the output. But you can see there's lots of sides to this. That's the actual shape there. You don't have to actually be able to visualize to do this problem. I'm going to claim that what I'm about to show you, you can do most of it without visualizing. At some point, sometimes it's nice to be able to visualize to make things easier for you. But you can see there's actually 5 sides. There's the green, the blue, the red, the purple, and the bottom, which I did in gray. Boy, that sounds complicated. Here's the process. So the process is this. I'll pull it up. This is what I give students, and we talk about this. Pretty much all of chapter 15 fits this. So what do? We first find the integrand. A double integral requires a region and a surface. So you go through. It's I feel bad showing this. Oh, I have a typo in my problem. I realize now. That would have made it a lot more fun, but that's supposed to be a y. Okay, so let's look. You search for your z's. You could even make yourself a machine. Now, if you take Math 224, we'll talk about what do we want to do if we want a different variable to be the output. But every problem we give you in the homework has z as the output. So we'll start there. The truth is you could try each one, but if we assume z is the output, then we're done with that step. We say the double integral. And the fact that it's z equals 0, it always finds the volume to the xy plane by default. So I don't need to do anything with the z equals 0. X squared plus 4y squared dA. Yay, step 1 done. Not bad so far. Step 2 is we draw the region. In other words, we're going to go through and draw every xy equation there that doesn't have a z in it and draw a region. Oh, here we go. So these two things happen immediately in these problems, meaning you take the z, you put it as the integrand, you start drawing the region. How do we draw the region? We draw x equals 2, we draw y equals 0, we draw y equals x. And those things only. Y equals 0 is right here. All the points where y is 0. X equals 2 is right here. All the points where x is 2. And y equals x is this line. And I could label all the sides, which doesn't hurt. No, wait, I'm done. That's it. So I'm not scared about all those equations because I have this plan of I'm going to have z be my integrand. I'm going to draw the region. Now there's a couple little subtleties I'll talk about. I'll do a couple more problems here. I'll do them in class. But then the problem becomes, how do you want to describe the region? And that's the big thing we'll be talking about in class. I just wanted to demystify that first step. Oops, sorry there. Trying to move this. The first step is not something to be worried about. We can very quickly fill in those pieces. The next step will be to whether we want to label it in terms of x or in terms of y. So pretty much all of these things I'm doing now are routine. You can program yourself to do it on every single problem. So it's controllable what happens. So that's the start there. So the only other thing, I would have the same picture drawn. Or I wouldn't necessarily draw it, but I would be thinking about it if I want to do it in terms of y. So every problem I do starts with this little setup. I draw my region, I label it in terms of x, I label it in terms of y, and then I make a decision about how I want to describe my bounds based off of that. Okay, and it gives the volume of that solid, which is pretty cool. And that's what will be the main thing I want to talk about in class. I just wanted to have a short video where I talked about what do you do with these word problems. Okay, let's look at another one. So just a few other things that can possibly happen along the way. So let's get rid of this. Let's look at another one. So assume the question says, I remember this on an old exam, find the volume of the solid bounded by, and then I'll just write the equations. So the list of equations were this. One of them was z equals 25 minus x squared. One of them was x equals 0, y equals 0, z equals 0, and I believe it was y equals 1. And the question said find that volume. So if you follow the routine I just said, you now know it's a double integral of this surface, and now we start to draw the region on the ground. Well, the region on the ground is y equals 0, x equals 0, y equals 1. So I draw these things. Y equals 1. I believe the problem actually said first quadrant, so it said they all were positive. And so what we've done is we found the integrand, we drew the given xy boundaries, and I'm confused. It does not enclose a region. Something went wrong. That means one of two things. This actually doesn't enclose a region, in which case the problem doesn't make sense, or it does enclose a region and somehow there's a boundary hiding in there. Now I'm going to show you a picture of this. This is this solid. It does not go on forever. In fact, it stops. It stops right here on this edge. Why does it stop? It stops because it runs into the ground. That's why they didn't give us another boundary, because they didn't need to. This thing only had 4 sides. So we need something in our process to find that when that happens. And the answer presents itself. So if you draw it all and it's not there, you need to find when the z's intersect. Do these intersect? Well, let's think about when they'd intersect. They'd intersect when this is 0, which would be when x squared is 25, which would be when x is plus or minus 5. Now the problem said, I didn't state the problem exactly. It said first quadrant, so I knew it was only positive. And that gives my other side. Aha. The first problem we didn't need that. They already gave us all the boundaries, but this one had required that additional step. And now I'll set this up. It's actually a rectangular region. I can set it up dx dy or dy dx. That's that next piece. Pretty cool. And it will find this volume. All right. And the boundary stuff is the stuff we'll be talking about in class. So I'm just talking about the setup piece. Let's look at another one. Let's see. I had several more in here. Oops. Here we go. So this one says, find the volume. Find the volume. This happens in 515.1, 15.2, and 15.3. These are just different types of regions, but it's the same setup. So find the volume of the region, the solid, sorry, bounded by, and it gives the following. Z, I think maybe it writes it this way. And Z equals 0. And that's all it says. So students are like, oh, yay, they didn't give me a ton of equations, but now I'm really confused. So step 1, get the Z by itself, minus this, that's my integrand. 18, that's my surface. Now I need to figure out the region on the ground. So step 1 is you draw any given XY equations. Are there any boundaries they gave? They didn't give me any. Well, shoot. What are we going to do now? Sorry, I messed up my screen there for a moment. Well, now we still follow the recipe. The surface must intersect, and you can see in the picture what I'm talking about. It just hits the ground and makes a circle. How would I find that circle? I would find when the z's intersect. What happens when these intersect? When they intersect, I get 2x squared plus 2y squared is 18. So I get x squared plus y squared is 9. They intersect to form a circle of radius 3. Lovely. So we're going to integrate above this. We're going to learn that there's a certain technique that's really good for integrating circles, but there's another example of that. So you draw the given equation, sometimes that's everything, and then you draw when the z's intersect. So it's a fairly simple approach to all the problems in chapter 15. Anyways, let's look at another one. So there's one question in the homework that says, find the volume and it says between, and let me think of what it says, x squared plus y squared minus z squared equals negative 22. It's hyperbolate of two sheets. And what's the other one? Z equals 5. So find the volume between the hyperbolate of two sheets and the plane z equals 5. What do we do now? So there's something a little different. This is the last kind of complicating factor, which is find the z's. Now in this case, there are too many z's. So we go, oh shoot, that means there are multiple surfaces I have to deal with, not just one. You can still follow the recipe. It's just now you're doing two different problems. So we're going to do the volume under z equals 5. That's one volume we'll have to think about. And we're going to do the volume under the other thing. So we'll solve for z. So let's see what happens. We get z squared is 22. I'm just rearranging a bit. And we get z is plus or minus the square root. And that's the moment where maybe we have to do some thinking, but I'll just come back to that in a second. But the point I want to make here is we can do that setup still. It's just we have, unfortunately, two different things to compute. We need to figure out what this is, and we need to figure out what this is, and then we need to put them together correctly. Okay? But still, the step is find the z's, set up your integrand. It's just there were two. Next, we draw any given xy equations. Are there any given xy equations? No. So it feels like we're stuck. But that must mean that these things intersect. So it's a little chase of logic. Where do those things intersect? Is it even possible? Yes, they do. I'm making up these numbers from memory, so I hope that I'm not making them up. I get this. I can add it over. X squared plus y squared is 3. Circle of radius square root of 3. So it's a pretty careful routine that works pretty well here to set this up. So everything appears to be happening above this circle and between these two things. So this circle is going to be what's going on here. If this seems too weird for you, here's a visual. So the hyperboloid of 2 sheets is that thing. The plane is this thing. Let me move this over somehow. A little bigger. We're finding the volume between them. The reason I only use the positive part of the hyperboloid of 2 sheets is because the negative part's not going to intersect with z equals 5. Okay, so let's get rid of those and just look at where they intersect. It's that thing. And ignore the orange thing. I'll talk about that later when we actually are finding the volume. So we want the volume between those. So strategy is we're going to find the circle on the ground is right there. That's where they intersected. We're going to find the volume from the gray region up to the green surface. And then we're going to find the volume from the gray region up to the blue surface, which was actually just a cylinder. And then we're going to subtract the bigger volume minus the smaller volume. That's it. Because of that, we don't really have to think that hard here. What I mean by that is, if you were having trouble visualizing, you could do this entire problem without visualizing anything. Meaning, you could put the appropriate bounds here, compute this number, compute the appropriate bounds here, compute this number, and do the smaller number from the bigger number. Bigger number minus the small. This will be the bigger number because we just saw that picture. This will be that cylinder. This will be the smaller. This double integral tool finds the volume to the xy plane. So if you're doing something between the two, you do the volume up to the bigger surface minus the volume smaller surface. That's it. So this technique I'm giving you, what I'm trying to show you is it applies to all these situations. Okay. There is a moment when a problem has complicated enough or the surface is weird enough that we might need to visualize. But anyways, lastly, find the volume. This is a different one. Between the following sphere and the cone. This is an interesting problem. I'm actually I have a group that's doing 3D prints of this problem. One student made this incredible video about this. But what's going on there? Step 1, find your z's. Double integral, square root. That's one of the z's. Step 2, find the other z. Well, the other z, if I solve for it, is the square root of 81. Those are the things that describe height. Finally, draw your region. Are there any given xy equations? No. So we need to find when these two things intersect. When do they intersect? Let's plug this in and see. When x squared plus y squared plus x squared plus y squared is 81. So that means 2x squared plus 2y squared is 81. So you get 81 over 2. And it's a circle of radius, whatever the square root of that is. Square root of 81 over 2 is 9 over the square root of 2. Draw that circle, and we got it. A complicated problem we've got. Has a pretty interesting visual. And as I said, I will have some cool 3D prints of this at the end of the term. But it's this. What we did is we took this circle. It doesn't look like a circle because I've distorted it a little bit so it looked better in the picture. They took this, they intersected above this circle. We're going to find the volume from the ground to the cone between them, and then the volume from the ground to the sphere. So we're going to find all of that volume between those two. And then separately, we're going to find all of the volume between those two. And I'll talk about that thing in the middle later. All right, hope that was helpful in terms of setup. Now I want us to get to where we can focus on the main thing, which is how do we figure out what these bounds are? And that's what we'll be doing in class. All right.